So in this last video about complex numbers, we're going to use what we now know about finding nth roots of complex numbers, and we're going to use that information to solve more general polynomial equations in a complex variable, z. Now, finding roots of a polynomial p of z, and you'll notice here that my variable is a complex number, means solving equations that look like this: p of z equals 0, and you'll know how to do this in the real case. So 2x squared plus 3x plus 2 is a polynomial. We could call that p of x, and we put that equal to 0, and what we're trying to do is we're trying to find the x values that make this thing equals 0. So we're doing exactly the same thing here, except we're using a complex variable z. So one way to do this is to factorise the equation and put each factor equal to 0. So for example, if I had x squared plus 4x plus 4 equals 0, that would be the same as x plus 2 times x plus 2 equals 0, and we could conclude that if those two brackets multiplied together equal 0, then one or the other of them must be 0, so x plus 2 must be equal to 0, and then that means x equals minus 2. So if we can factorise it, we can use that argument, and in the quadratic case, if we can't factorise it, we use this thing x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So you'll remember that formula from school, I'm sure. When we're trying to solve a polynomial over the reals, some quadratics have roots because they can be factorised into these linear factors, and that's an example that I gave you before. Sometimes you can't see them straight off and you use this relationship, but they're still factored into linear factors. Others have no real roots because you can't factorise an equation like that over the real numbers. And what that means is, and if you think about this by the graph, if we've got a situation where our polynomial has two real roots, then it'll be a graph that looks like this, and the two real roots will be where the graph of the polynomial crosses the x-axis. So that's what happens if we've got two real roots. If we've got one real root, then the parabola might look like this. So it will touch the axis, but it won't cross it. So that point there is the point where it has one real root. In the other case, where it has no real roots, then we might have something that looks like this. So the polynomial might sit above the x-axis and it doesn't cross it anywhere, so we can't find any x that makes that thing equal to 0. It's a little bit different when we're trying to factorise polynomials over the complex numbers though, and it's really neat because we have this beautiful result called the fundamental theorem of algebra. Now, I can warn you now that anything that's called the fundamental theorem of anything generally means that it's a very important result, and this is no exception. So if you have a polynomial where the variables are complex numbers and the polynomial has degree n, and what we mean by degree n means that the highest power of z is n, in that polynomial. So if we have a polynomial of degree n and the variables are complex variables, then this can be factorised into n linear factors that look like this. So we can always factorise our polynomial into n linear factors in this fashion. Now remember that we couldn't do that in the real case. And that was clear from the example that we had on the previous page, x squared plus 3x plus 4 we can't factorise that into linear factors. And so in the real case, when we're looking at a real variable, this is as good as it gets in terms of factorisation. But if we had a similar polynomial in a complex variable, the fundamental theorem of algebra says that I can find two linear factors to factorise this polynomial into. So of course what that means is if you've got a polynomial of degree n, then like this one, every linear factor will give you a root of the polynomial, because when z equals alpha 1, that will be one solution. When z equals alpha 2, that will be another solution. So every term in this product will give you one of these solutions, which we call a root over c. So the result says that every polynomial of degree n has exactly n roots if we try and solve that in the complex numbers. Not all of the roots though will be distinct, so you might get some repeated roots. Okay. The other thing that happens is if you've got this polynomial in Z, complex numbers, and the coefficients of all the terms are real numbers, so they have imaginary part of the coefficients equals 0, so they're just real coefficients, then it turns out that any non-real roots, and what we mean by that are roots that have imaginary part not equal to 0, so any non-real roots of the polynomial occur in complex conjugate pairs. So if you have x plus iy as one of your roots, you know that x minus iy will always also be one of your roots. And we saw an example of that last week when we were factorising a quadratic. So I'm going to do one example for you, and then there's lots of other examples for you to try yourself at home. So I'm going to do one example for you, and then there's lots of other examples for you to try yourself at home. So here's the polynomial that we're going to consider. And the first question is, how many roots do you expect this polynomial to have? So the theorem on the previous page said, fundamental theorem of algebra said, if you have a polynomial of degree n, then you can expect to get n roots. Okay, so this polynomial has degree 3. The highest power of z in the polynomial is 3. So the fundamental theorem of algebra says that we'll get 3 roots. Okay. Now the next thing we need to do is to find those roots. So we're going to factorise p of z. So let's think about p of z. P of z is, I'll take that off so we can see it. P of z is z cubed minus 3i z squared minus 2z. And you can see that there's a z in every term, so I can write this as z times z squared minus 3iz minus 2. And now I need to factorise this bracket. Now I can't see how to do that immediately, so I'm going to use the quadratic formula, z equals minus b plus or minus the square root of b squared minus 4ac over 2a. So let's put this down in our case. So minus b is 3i plus or minus the square root of b squared, so that's 3i squared, minus 4, well, A is 1 and C is minus 2. And that should be over 2A. So 2A is just 2 times 1, so that's 2. So this is 3I plus or minus the square root of 3I squared is just minus 9. And this is, there's 2 minuses, so that's a plus. So that's going to be plus 8 on 2. So this is 3I plus or minus square root of minus 1 over 2. And the square root of minus 1 is just I. So this is 3I plus I over 2, or 3I minus I over 2. Okay? So we can just simplify this a little bit. I'm just running out of room here. So 3I plus I on 2 is just 2I. 3I minus I on 2 is equal to I. So the factors here are going to be Z staying out the front, then Z minus 2I and Z minus I. Okay, so that's how we factorise the polynomial P of Z. In the next item, part 3, so this is still part 2. So in the next item, part 3, we need to find the roots of P of Z, and we do that by putting P of Z equal to 0. So we're going to use this factorised form. Let me just clear some of this up so I've got some more space. All right, so we've got Z times Z minus 2I, Z minus I, and that's going to equal 0. So when you've got a product of things being equal to 0, at least one of those things, maybe more than one, but at least one of those things has to be 0. So how is that going to work? Well, Z equals 0, we'll make that term 0. Z equals 2I, we'll make that term 0. And Z equals I, we'll make that term 0. So the roots of PZ are 0, 2I, and I. In the last part, we want to verify our answer by showing that if I put the Z's back into the polynomial, I actually get 0. So let's do that. So I'll write down the polynomial again. So P of Z is equal to Z cubed minus 3I Z squared minus 2Z. And the roots of the polynomial are Z equals 0, Z equals 2I, and Z equals I. So verifying this just means that I have to go through each of those things one at a time and make sure I actually get 0. So when Z equals 0, P of 0 equals 0 cubed minus 3I 0 squared minus 2 times 0. So this is certainly 0 minus 0 minus 0. So that equals 0. So the first one works. P of 2I equals 2I cubed minus 3I 2I squared minus 2 times 2I, and we have to work all that out. So 2I cubed, well 2 cubed is 8, I cubed is minus I. In the next place I've got 3I times 4 times minus 1, so I've got minus 4, and then I've got minus 4I. So if we pull all this together, this is going to give me plus 12I and minus 4I. So if you simplify that, you get 0. So it works in the second case as well. And PI equals I cubed minus 3I times I squared minus 2 times I. So this is equal to minus I. I squared is just minus 1, so it's plus 3I minus 2I. And again, you get 0. Okay. So that's the end of the example. So it's not too hard. And going back to the page before, just treat it like you would normally treat any polynomial that you're trying to solve. And now the only difference is now that when you get to this b squared minus 4ac underneath that square root sign, if that turns out to be negative, then you can continue on. Okay, so there's some other questions for you to look at. The hint for this one is, well, this is a polynomial of degree 4. So how many roots do you expect to get? That's hint 1. Hint 2 is what if you write z squared equals w? See if that helps if you can't think of how to proceed with that one. That's a continuation of the example before. And a cubic for you to solve, and then you're done. So there's a couple of examples there for you to look at, and then you can continue on and do some of the questions in topic 3. When you get to the end of this video, we'll be going over this material in class, and this is the end of complex numbers now. So I strongly suggest that you go back and make sure that you understand all of the things that we were doing here. Because we won't really be doing much more with complex numbers in the rest of the subject. So if you don't get this under your belt now, by the time you get to the exam period, you might be finding that it's your memory's a little bit hazy and you can't remember why you did things. So it's a good idea to make sure you keep up to date with the topic, finish this one off, and in the next video we're going to start doing some work on differential calculus. We'll do a tiny little bit of revision at the beginning, but not very much. All right, see you Thursday.